Washington State University. Go Cougs!
Hello and welcome back to our course on statistical inference. We're in Module 4 where we are learning how to evaluate the models that we are learning. And in Part 2 of Module 4, we're going to look at a technique called cross-validation, which gives us a better estimate of how our models will work in the real world, and also a better idea of how good the classification method is that we're using to learn those models. So up till now, we've been using what's called sample accuracy to evaluate our models. Namely, we're given a sample data set X, and not only do we learn our models on X, but we also test the models on X as well. And so generally, allowing the learning algorithm to learn a model on the exact same data it's going to be used to test that model is going to generate overly optimistic accuracies, or we wind up learning too specific of a model because we're training it on all of the training data as opposed to just some of it. So a better approach is to evaluate what's called generalization accuracy, and the basic idea is to test the learned model on data that's not in the training set, so that it hasn't seen the data that it's being tested on. And not only is that a more realistic setting as we deploy this model in the real world, but it will give us a more accurate measure of how accurate it will be in that real world setting. So one way to generate a separate set of data that we'll set aside for testing is to actually separate our original data into two sets, a training set and a test set. Sometimes that test set is called a validation set. So we can partition our original data into a train and a test set, and then we fit the model or train the model on the training set. But when we go to compute the accuracy, we compute it based on the test set. We make predictions on the test set and measure its accuracy. Now we can do that once, which is good, but we can actually do even better if we repeat that process multiple times, each time choosing a slightly different training and testing set. So we do that multiple times and compute all the accuracies, and so the final estimate is the average of all of those accuracies. Now, one problem with this approach, as it's typically implemented, is that each time we generate this training and testing set, it's essentially a random sample from our original data set X. And therefore, as we do this multiple times, there's a good chance that the same example will show up in multiple test sets, meaning that the learning algorithm will be either over-rewarded or over-penalized based on whether it gets that example correct or wrong. And this is, in general, a source of bias in our statistical estimate of how good this learner is, because the test sets may overlap. So we'll eventually get rid of this bias, but we should be aware that it is there if we're using this multiple train test split approach. Now, scikit-learn has a method built in for generating these training and testing splits for us just by passing in the data. And so let's take a look at how to use that to generate one of these generalization accuracy estimates. So in the validation Python file, you'll see fairly common techniques we've been using. We're loading in the read data method. We'll be using the naive Bayes classifier just because we've kind of been using that throughout. We'll load in our metrics so we can compute those, and then we'll load in this train test split method from the model selection module. Next, we'll read in our data, our sensor data. Again, we'll read in all 9 features and the classes, of course, just as we've done before. And then we've defined this function here called validate. And basically, validate is going to do one iteration of this train test split. So you can see each time we call it, it's going to take our training data, X and Y here, and split it up into X train and Y train, and then X test and Y test. And it does that according to this fraction that we pass in. In other words, 33% or a third of the data will be in the test set, and the other 2/3 will be in the training set. So given that we have, 56 examples, we're basically going to get about 19 or so in the test set, and so about 37 in the training set. And that's fairly typical. You want a little bit more data to train on in order to get a robust classifier. So once it divides up the data, again, this is a random division. It creates an instance of our naive Bayes classifier. It trains it on the data, on the training data, but then it tests it on the test data, and then computes the accuracy score of the predictions on that test set. So again, this is on data that isn't part of the training and the learner has not seen it. So that is one pass through this train test split process. And down here is the code that's going to run through that multiple times. In this case, we're going to run through it 100 times and then collect the accuracy, sum it up over all of the calls, and then compute its final average value. And that's what we report. So if we were to run this, we would see the output here of the accuracy split. And you can see that it's different. I'll run this code a little later because I want to add some more to it. But at this point, we will get different values because, again, this, even after 100 tries, this is a random element of this train test split. So each time we run it, we'll get slightly different results. But overall, this should be a little better estimate of the final accuracy for at least the naive Bayes classifier on this data set. Now back to this problem of having the same examples show up in different test sets. There's a method we can use to avoid that, and that is called cross-validation. And that is the topic of this part because cross-validation is one of the main methods for evaluating a learning algorithm. So basically what we're doing here is instead of randomly choosing the training and testing set, we're actually going to divide up our data set into K subsets, and those subsets are disjoint, so we're just chopping it up into K generally equal parts. And then we run through each of those K parts, let I range from 1 to K, and these are basically the trials that we're going to go through. But each time we go through a trial, we're going to use a different one of these subsets as the test set. So the test set for the ith trial will be the subset I, or the ith partition. And then the training set will be all of the other data. So the original data minus the examples that are in this subset. And then as before, we train the learning algorithm on the training set and then compute its accuracy on the test set. And then we average all of those accuracies to get our final estimate of the accuracy of the model. Now, by doing this, as you can see, the test sets are now no longer going to overlap. And there's also not any randomness in this process, so we'll get the same result every time. Now, this whole process is generally referred to as K-fold cross-validation, and each of these trials is called a fold. And as we said, each fold is using a different test set. Obviously, the training sets may overlap quite a bit, but at least the test sets will not, and that will remove some of that bias in the estimate. Now, scikit-learn does have a method for doing the cross-validation for us. In fact, it's a very nice method in that we just pass in the classifier and the data, and it does all the work for us. And we also tell it the value of K. So let's see that in action. So here's the last part of our validation Python program. We go ahead and load in the cross-validation score method or function, and that function takes a classifier and the original data, both the features and the classes, and then the number of folds, or in this case the cross-validation value, which is how many folds. Now note that we're not training or fitting this classifier, we're merely kind of creating an instance of it. And then inside of the cross-validation score method, it will actually divide up the data as we saw and fit this classifier to each training set, test it on each test set. In this case, we'll do it 3 times, and it will return the accuracy values for each of those 3 folds. And then finally, we'll compute the mean of all those accuracy values and report that as the final cross-validation accuracy. So this is the value we're going to get, but let's go ahead and demonstrate that. So in our source directory, we're interested in this validation Python file. So let me run that. So first you see the accuracy we get by running 100 trials using the train test split, and then the second result is the cross-validation accuracy. Now I can run this again, and you'll see we still get the same cross-validation accuracy, but the split accuracy is slightly different. Again, this is because that split is randomly determined, and even though we're averaging over 100 trials, we still get a little variability in the result. Run it a few more times, and starting to see some of the values repeat, but in general we'll get different values there, but the cross-validation value stays the same. And this is useful for when we're trying to validate results. If there's no randomness in the process, we can be sure that we're getting the same value everyone else would get if they ran it. So let me go back to the notes. So as we saw in this case, the cross-validation accuracy about 94, 95%. We note that the sample accuracy, so again, if we evaluated naive Bayes on the entire data set, so we trained it on the data set and evaluated it on the same data set, we actually got a slightly lower accuracy, which is unusual. Typically the sample accuracy is overly optimistic. But in this case, we have very few examples. And in fact, if you note, for 3-fold cross-validation, each of those folds is essentially using only 19 of the examples for testing. And so that's really not a lot. We don't have much data to begin with, only 56 examples. Normally we would have hundreds or thousands of examples. And we'd have much larger training and testing sets, and would get a little bit more consistent results. But in general, this is a very good way to evaluate a model by running the k-fold cross-validation. Typically, values of 3 or values of 10 are used depending on how much data you have. But that provides a fairly unbiased estimate of how well the model is expected to work, even when it is run on data it hasn't seen before. Okay, so that pretty much completes how much we're going to evaluate a single model or a single classification method. But the next question is, how do we compare different methods? For example, how does naive Bayes compare to, say, decision tree or neural network? And that takes us into the topic of hypothesis testing. And so in part 3, we will cover that, where we will learn a fairly rigorous way to be able to answer the question, which classification method is best?